Hello and welcome to another video. Today we'll be doing our first formal video on derivatives. So I know we did our limit definition of a derivative prior, and that will give us the same answer, but we are still using limits, and from now on we're going to use very specific rules that help us get derivatives much faster. But just in case you missed those videos, I implore you to check them out for a more detailed version of everything covered, but just keep in mind that the definition of a derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. And they'll give you a function and you'll plug things in and you'll find a value that's the same thing of what we're going to do in these videos with numerous tricks. And also understand really quickly that the derivative, or what's going to be called f prime of x usually is what it's referred to as. This is the same thing as the derivative. You can also use something over dx, which is the same thing as well. It's just this is the most common way it's referred to. So the derivative is equal to the slope of the tangent line. And that's what we were finding last time. We were finding that slope and we were finding the equation after. But keep in mind that the derivative is the slope of a tangent line. It's just we won't always be finding this slope always, but there will be numerous problems where we will do that. And so it's important to keep that in mind. But from this video is going to be an intro to derivative processes in general. So I'm not going to go so much into every single detail, but I will give you the general consensus of what everything would be. So let's first go over what's called the power rule. One of the most important rules you'll go over. And that's just because it can be used in so many situations, most notably polynomials, rationals, and radicals. But let's just go over each one separately and I can show you what I mean. So if we had this function, let's say if it was f of x equals to x cubed, and we wanted to find its derivative, we would of course say f prime of x. And the rule for the power rule is as followed. We're going to have x to some power, and that can be turned into power rule. We bring the n down, multiply it by the x, and we subtract n by 1. And that gives us the power rule. That's all we have to do. So for example, if we wanted x cubed to follow this rule, well, we would bring the 3 down. Let's make that a little more clear of a 3. So we would bring the 3 down, so 3, and then we would subtract the 3 by 1, which would make it 3x squared. And that's all you have to do. Let's try something similar. How about x to the 10th power? So something kind of large. Well, doesn't matter how large it is, we can do the same exact thing. How about we bring it down, that's the 10, then we subtract 10 by 1, that's 9. Let's try another one. How about x to the 5th power? Well, let's bring the 5 down, and then let's subtract the 5 by 1. So we get 5x to the 4th. So all of them follow a very similar pattern, if you notice. And that's just because the rule is very consistent. Let's try something a little bit different. How about if we have a constant in front of the x? Does that matter? Well, let's see. How about if we had 4x squared? Would that matter? Well, let's see. If we had 4x squared, we could then bring the 2 down, but let's keep the constant there. So we bring the 2, well, that's a 2, and then we subtract 2 by 1, well, that's to the 1st power. And then we would multiply 4 by 2, because they are multiplying at the start. So we'd say f prime of x equals to 4 by 2, which is 8. And then, of course, to the 1st power is just, we kind of usually leave that invisible. So it become 8x. And this is a good time to realize that if we have x squared, actually, we get x as a answer. Similarly, if we, let's say if we had, what if we had 7x? How would that be? Well, let's test it and see what happens. So if we were to, and remember this is to the 1st power, so if we were to have the 7, carry that over, then we bring the 1 down, that's the 1. Okay, so far so good. Then let's subtract 1 by 1. Well, 1 by 1, that's 0, interestingly. Okay, that's to the 0. Well, what's x to the 0 again? Well, if you remember something like e to the 0, if you remember, is 1. So anything to the 0 power is 1. So since we know that, we can say that 7 multiplied by the 1, which again we kind of can leave out at this point, because 7 by 1 is just 7. And then we leave. And I suppose what you want to do is you could keep writing this to show your work just so that you could see it. But just know that since 1 by x is x, and then x to the 0 power is 1, really this is 1 by 1, so we have 7 by 1, which is 7. Which means that in all cases, if we have an f of x, and let's just say we had f of x equals to x, well, we know that f prime of x will always be 1 because of that process. So just keep in mind the two outliers so far is that if we have some sort of x squared, we know that it just turns into an x, and if we have an x, it turns into a 1. Well, going on this kind of oddball train, what if we had something like f of x equals to, let's just say, a constant. Let's just say it was 7. What happens now? Well, we have to kind of extrapolate a little bit, because we know, I'll just tell you right now, that a derivative of any constant is 0. But to show you why that is, we have to rewrite this a little bit. So let's say that f of x of 7, let's say that's it's going to be 7x to the 0 power. That might look weird, but we already know that x to the 0 power is 1, and 7 by 1 is 7. So this is perfectly fine. We can rewrite it like that. Okay, well, let's take the derivative of that then, if they're the same. So if we were to bring the 0 down, well, that would be 7 multiplied by 0, x in 0 minus 1 is to the negative first power, and we know that it's going to be 1 over x, but it doesn't really matter because this whole thing is 0, and 0 by anything is just 0. So we actually end up getting that whole thing equals to 0. And that's why a derivative of any constant, it doesn't matter what it is. It can be e, it can be pi, it can be 2.7. It doesn't matter what the number is. If it's a constant, if there's no variable, it's just 0. So just keep that in mind. Okay, let's move on to something different. Let's say we had rational functions instead, because we actually can use them for rational function. It's just not always clear right away. So if we had 1 over x squared, can we use the process? Well, not yet, because we don't have enough. It's not in the right form. So we know from experience that we can rewrite 1 over x squared as essentially, we can write that as x to the negative 2 power. The same exact thing. Well, now that it's the right way, let's take a derivative of that. So if we bring the negative 2 out front, and then we subtract negative 2 by 1, wait a minute, negative 2 minus 1, well, that's just kind of like adding, isn't it? It is. So rationals, when you subtract, you're kind of adding to their power a bit. So this is the answer, negative 2x to the negative third power. However, some teachers don't like you to leave things in this negative exponent way, so if we wanted to rewrite that, we just have to put the exponent back below. So the negative 2 can remain on top, it's still a constant, but the x cubed will go on the bottom, because we're just moving it back the way it was at the beginning. Okay, let's try something similar then. How about just maybe, how about 2 over x? Does the same thing apply? It should. Let's rewrite f of x then. So if we rewrite that, that'd be 2 times x to the negative first power. So if we take the derivative of this, well, we know that's going to be 2. Bring the negative 1 out front. Then x, we're going to then subtract by 1. So negative 1 minus 1 is negative 2. And now we can just kind of simplify just like before. And if you notice, it's just like when we had constants here, we're just having negative exponents, but the same process applies. 2 times negative 1 is negative 2, and then we're just going to keep that negative exponent the same. Okay, so now let's just rewrite that if we had to, if your teacher made you. It's not too bad to do. We keep the negative 2 out front, we bring this down, then it returns into x squared. So this is the same thing, we're just rewriting it. 2 over x squared. So the same thing applies. We can still take the derivative even if there's a constant of a rational. Let's try something of a similar vein. So let's say we had radicals, because radicals are the last kind of function we can use the power rule for right away. Let's say we had root x. Do we know what root x is in terms of power? Because we can't do it like this. We don't know what power it is. Well, we know that root x is x to the 1/2. If you don't remember why that's the case, keep in mind that on the outside here, we have a 2. It's just sort of usually invisible for a square root. And then on top of the x, there's a 1. So whenever we're dealing with fractional exponents, if we have a root, the 2 is the bottom number of the fraction, or the outside number, and then the one inside turns into the top of the fraction. Okay? So if we were to take the derivative of that, because we can do that now, well, let's do the same exact process. So let's put the 1/2 out front, then let's subtract 1/2 by 1. Well, 1 would be the same thing as 2 over 2. We know that too. So 1/2 minus 2 over 2 is a negative 1/2. And it can be negative, that's fine. So let's put the negative out front, and then let's simplify it a little bit. Because technically, you actually got the answer. That's perfectly fine. But some teachers, again, want you to simplify that a bit. So we know that we can put the 1 up top here, because we know that the x flips down to the bottom for negative exponents. So x to the 1/2 power. And we also know that a 1/2, well, that's the same thing as 1 over 2. So that works, but we can go a little bit further if we wanted to. We can say that that's going to be 1 over 2, and then the x to the 1/2 is the same thing as root x, like we already figured out. So the answer actually is 1 over 2 root x. Okay, so that's your derivative. And because you might be seeing a lot of the derivative of a square root, I would just try to commit that to memory. You'll see it a lot. Okay, let's try a little more difficult one while we're already here. So let's try something like the cube root of x squared. So this might seem weird, but this is the same thing as something like this. We just have to think about our rule of fractional exponents. So if we have something on the outside, we know that that's the bottom number. So the 3, the cube root, we know is the bottom. If it's x squared, we know that the inside number is on top. So that's a 2. So this is the same thing as x to the 2/3 power. Well, we can definitely turn that into an answer. So let's bring the 2/3 out front. Then let's go ahead and subtract by 3 over 3, because that's 1, remember. So 2 over 3 minus 3 over 3. Well, that turns into negative 1 over 3. So that turns into negative 1 over 3 instead. So if we were to do that, well, now we can just simplify it. So if we were to do that just like before, well, we know that the 2 can go on top since we're dealing with the fraction again. So 2. We know that the 3 can go on the bottom, so it's still 2/3. We know now that x it turns into some sort of root, but what is that exactly? Well, we can figure that out pretty quickly. So we know that from experience, the bottom number is what goes on the outside, so we have a little 3 here, a cube root, and we know that the 1 is on top, which we could get rid of if we want to, which means that the final answer turns into 2 over 3 cube root of x, and that's your answer. So just to let you know, you can do this a variety of ways. You just have to follow the same rules for exponent of radicals and rationals, and you can get the same and pretty quickly the same answer as you had just standard polynomials. So these are all the very basic kinds of ones you'll have for standard x's when they're alone. I'm just going to come right back for things involving trig, so we can know the basic trig ones as well. So when we're talking about the first part, it's important to know some of the trig ones since there actually are no tricks or rules for them. They really are just things you have to memorize. And because you'll be using them quite a bit for derivatives, it's important to know the relationships. Okay? So the first one is, what is the derivative of sine of x? So if we wanted to know if we had f of x equals to sine of x, well, the derivative of sine of x will actually just be cosine of x, okay? And if we had something like, let's try cosine now. So what's the derivative of cosine? Well, the derivative of cosine turns out to just be basically negative sine of x. So sine and cosine are related, as you can see. So sines is cosine of x, and cosines is negative sine of x. Okay, well now that we're on a roll, let's see if we can do the other ones too. So if we had tangent, what would tangents be? Well, tangent's derivative is actually secant squared of x. That is tangent's derivative. And if you recall your trig relationships, where tangent and secant actually share a relationship in terms of the identities, it kind of makes sense that they might be included in the derivative as well. And similarly, let's kind of go to cotangent because they have a similar idea. So cotangent's derivative is going to be negative cosecant of x. So negative cosecant squared of x, I apologize, is the derivative of cotangent of x. Okay, now let's try the other last ones while we're already here. So your derivative of secant x is going to be secant x tangent x, and that's them being multiplied by one another. So secant x tangent x is your derivative of secant. And similarly, if we had cosecant of x, well, its derivative will just be negative cosecant of x cotangent of x. So as you see, although you have to memorize these, they actually do kind of follow a pattern with one another. It's important to realize that all of the C ones, so cosine, cotangent, and cosecant, all have negatives attached to them, whereas everyone else doesn't have a negative. Okay, but other than that, they do follow a very similar pattern, where you see cotangent and cosecants are very much related, and secants and tangents are very related as well. Okay, so although you have to memorize them, they aren't too bad to understand. Okay, so introducing these usually works decently well. So if I were to ask you something like, if we had f of x equals to 2 sine of x, could you solve that for me? I think you could. So that would be 2 multiplied by the derivative of sine, which we know is cosine, which would mean that our derivative is 2 cosine of x. So not that bad. Let's try something similar. What if we had 3 tangent of x plus 2, how about we said secant of x? So what would f prime would be? Well, let's just keep the constant. So 3 tangent's derivative is secant squared, and secant would be secant tangent. So secant tangent x. And we could just rewrite that if you'd like to 3 secant squared of x plus 2 secant tangent of x. And if you'd like to, you also could take out a secant. That would work perfectly fine, but we won't do that at this step right now. And let's try one more, kind of practicing the general idea. What if we had, let's just say, how about 4 cotangent of x plus 3 sine of x. So if we wanted to find f prime, just like before, we would carry the constant, so 4, and we know that cotangents is negative cosecant squared of x, and we know that sines is just cosine, so 3 cosine of x. Next, we would just carry the negative though, so if anyone gives you a negative, we just have to carry that over. So negative 4 cosecant squared of x plus 3 cosine of x. And this would be the basic idea of how you could really solve any normal trig derivative if they're just giving you adding or subtracting. If we start getting into multiplication or division, there's different rules for that, but we'll get to that at a different time. Okay, we're going to be doing the derivative of the tangent lines now. Just before I forget to, we went over all the basic trigonometry derivatives as well as the power rule and how it can be used. But because it's so simple to do, I do want to quickly show you a derivative of e to the x. So although normally exponentials and log functions require their own rules to understand the derivative, e to the x is very special. e to the x's derivative is just itself. It's the only derivative where its derivative is always itself. So if we just have e to the x, its derivative is just going to be e to the x again. So just to show you really quick, in case that comes up, that's the idea of that. But normally, all other exponentials and all other logs can't be solved like that. So let's try something else now. Let's talk about the equation of the tangent line using, though, a little more advanced functions, because now we understand the power rule. Now I won't use trig yet just because I want you to get used to understanding, but we can use that coming up. So if we add the equation, let's just say, how about x to the fourth, let's just say minus 2x squared, and let's just say it was plus 1. How would we solve something like that? Well, we know that from our power rule we can do that relatively quickly. So we know that we bring the 4 down, that turns into 4x cubed, subtracting 1. We have a 2. We'd multiply it by bringing the 2 down. Then we'd subtract by 1, which turns just into to the first power. And we know that the derivative of any constant is just going to be 0. So if we had, let's just say, 4x cubed, we'll just simplify it a little bit before we have to solve it. That turns into 4x. And then, if we wanted to understand how to find the tangent line to this, well, remember, when we were finding it from the definition, we just had to find an x point, so they had to give us a point. Let's just say in this case, the point is going to be, let's just say 1, 0. So if the point was 1, 0, how would we solve this? Well, we would just have to put in the f point of the x, so that would be 1. If we plug it into the derivative, we will get the slope. So we know that it'd be 1 cubed minus 4 times 1. And if we had 1 cubed, that would be 1 again. So 4 times 1 minus 4 times 1, which of course would be 4 minus 4, which is 0. So in this case, the slope, or the m value, is going to be 0. Now, if we wanted to find the equation of the tangent line, not just the slope, just like before, we would use y minus y1 equals to m times x minus x1. This is in point slope form, but we want to rearrange this into intercept form. So we would have y minus 0, the y point, equals to the m, which was 0 in this case, and we'd have x minus 1, which was the x point. So if we did this out, we would get that everything here would be 0, so because 0 by anything is 0, so 0, and if we added 0 to 0, we would just get that y equals to 0. So in this case, we just have a line, or a horizontal line, for the slope, but it's not always a horizontal line. Usually it's some sort of function. So let's try one more tangent line problem so we can get used to doing them for functions. So let's just say we had the function f of x equals, let's just say x to the maybe negative 2/3, just to get used to doing them with rationals even. Now in this case, it's already been given to you in the fractional form, but if it was given to you in root form, you would just put it into fractional form to take the derivative like normal. So we just bring this down, so negative 2/3 x. If we subtract negative 2/3, if we subtract 1, which would be 3/3, we'll get this is just going to be negative, basically 5/3, and that would be perfectly fine for an answer. And let's just say we wanted to put this in for the point 1, 1. Now usually you would want to put this into its original form just so you don't get mixed up in terms of what the answer is. But because we have 1, and for the sake of this problem we're just going to use something that can give us a pretty simple line. We'll have negative 2/3. If we put 1 to any power, well, that just turns into 1. So this would be the same thing as essentially 1 times negative 2/3. So this turns into just negative 2/3 for the slope. So then if we were to solve this, we would again want to use y and then minus the y point, so 1 equals to the slope, negative 2/3. And then we would just go ahead and quickly say that would be multiplied by the x minus its 1 as well. Now we can simplify. That would be y minus 1 equals to negative 2/3. And then we have x minus 1. Now we would distribute the negative 2/3. We would say that it's y minus 1 equals to negative 2/3 x. And this times 1 will again just give you a positive 1 because it is a negative there. So plus 2/3. And then if we were to add 1 to this, so add 1 to 2/3, remember that 2/3 is actually 2/3 plus 1 would be 3/3. So 2/3 plus 3/3 will give you 5/3. So our equation is negative 2/3 x, basically plus 5/3. And this would be the same thing as when we found out the limit definition and we found the equation as well. So this was a very brief introduction to all the basic things you might find when you're first starting with derivatives. Know that there are other things you could do, and they're not always using just x terms and using them in this exact way, but these are the things you'll find in a general basis. There'll be other concepts will be covered soon, going a little more deeply into the trig ones, to the exponentials, to the logs, that we can apply them to other forms as well. But for now, this will be an introduction to the derivative process. Hope this helps.